Let's discuss key considerations within the scope of the National Electrical Code, specifically focusing on the concepts often addressed in Chapter 2, understanding that we're doing so without direct access to a specific updated online resource. Chapter 2 of the NEC primarily covers wiring and protection, a cornerstone for safe and effective electrical installations. It establishes the general requirements for the use and identification of listed or labeled equipment. Understanding the scope of these requirements is crucial for electrical engineers and electricians alike. One of the primary things it addresses is the use of proper wiring methods. Wiring methods approved by the NEC are outlined extensively, encompassing cable types like non-metallic sheet cable or NM cable, often used in residential settings, and armored cable or AC cable, offering mechanical protection. Electrical metallic tubing, or EMT, and rigid metal conduit, or RMC, are also common methods, especially in commercial and industrial environments. Each wiring method has specific applications, limitations, and installation requirements detailed within the code. Understanding these specifics is critical for selecting the appropriate wiring method for a given installation. Cable types such as Type NM, non-metallic sheet cable, are typically used in dry locations within residential buildings. They are available in various conductor sizes and numbers of conductors. The NEC specifies the allowable ampacities for conductors based on their size, insulation type, and the ambient temperature. It is important to note that ampacity is the current carrying capacity of a conductor, and exceeding this limit can lead to overheating and potential fire hazards. Type AC, armored cable, provides a degree of mechanical protection and is suitable for use in both exposed and concealed work. It is commonly used in residential and commercial buildings. The armor provides protection against physical damage to the conductors. Type MC, metal-clad cable, is another type of cable that offers enhanced mechanical protection compared to Type AC cable. It is often used in industrial and commercial applications where greater protection is required. Conduit systems, such as electrical metallic tubing, or EMT, intermediate metal conduit, or IMC, and rigid metal conduit, or RMC, provide a high degree of mechanical protection and are often used in exposed locations or were subject to physical damage. EMT is a thin-walled conduit that is easy to bend and install. IMC is a heavier-walled conduit that offers greater protection. RMC is the heaviest walled conduit and provides the highest level of protection. The NEC specifies the requirements for supporting and securing cables and conduits. Cables must be supported at intervals specified in the code to prevent sagging and potential damage. Conduits must be securely fastened to structural elements to ensure they remain in place. The NEC also addresses the requirements for boxes and fittings used in electrical installations. Boxes are used to enclose electrical connections and provide protection for conductors. Fittings are used to connect conduits and cables to boxes and equipment. Boxes and fittings must be listed for the intended use and must be sized appropriately to accommodate the number and size of conductors. Overcurrent protection is another critical aspect of wiring and protection. Overcurrent devices, such as circuit breakers and fuses, are designed to protect conductors and equipment from overloads and short circuits. The NEC specifies the requirements for overcurrent protection, including the selection of appropriate devices based on the ampacity of the conductors and the rating of the equipment. Circuit breakers are electromechanical devices that automatically interrupt the flow of current in the circuit when an overcurrent condition occurs. Fuses are overcurrent protective devices that contain a fusible link that melts and opens the circuit when an overcurrent condition occurs. The NEC requires that overcurrent protective devices be readily accessible and properly labeled. This ensures that they can be easily located and operated in the event of an overcurrent condition. Grounding and bonding are essential for electrical safety. Grounding provides a low impedance path for fault current to return to the source, which helps to trip overcurrent protective devices and prevent electrical shock. Bonding is the process of connecting all metal parts of an electrical system to create a continuous electrical path. The NEC specifies the requirements for grounding and bonding, including the use of grounding electrodes, grounding conductors, and bonding jumpers. Grounding electrodes are used to connect the grounding system to the earth. Common types of grounding electrodes include ground rods, ground plates, and metal underground water pipes. Grounding conductors are used to connect equipment and enclosures to the grounding electrode. Bonding jumpers are used to connect metal parts of an electrical system to ensure electrical continuity. Surge protection is becoming increasingly important to protect sensitive electronic equipment from voltage surges caused by lightning or other electrical disturbances. Surge protective devices, or SPDs, are designed to limit the magnitude of voltage surges and divert the excess current to ground. The NEC includes requirements for surge protection, including the location and installation of SPD. SPD are typically installed at the service entrance of a building to protect the entire electrical system. They can also be installed at individual branch circuits to protect specific equipment. The NEC also addresses the requirements for wiring in specific locations, such as hazardous locations, wet locations, and healthcare facilities. Hazardous locations are areas where flammable gases, vapors, or dust may be present. The NEC specifies special wiring methods and equipment for use in hazardous locations to prevent explosions and fires. Wet locations are areas where water or other liquids may be present. The NEC requires the use of waterproof wiring methods and equipment in wet locations to prevent electrical shock. Healthcare facilities have unique electrical requirements to ensure patient safety. The NEC specifies these requirements, including the use of isolated power systems and ground fault circuit interrupters, or GFCIs, in patient care areas. Ground fault circuit interrupters, or GFCIs, are devices that detect ground faults and interrupt the flow of current to prevent electrical shock. The NEC requires the use of GFCIs in wet locations and other areas where there is a high risk of electrical shock. Arc fault circuit interrupters, or AFCIs, are devices that detect arc faults and interrupt the flow of current to prevent fires. Arc faults are dangerous electrical conditions that can occur when insulation on wires becomes damaged or frayed. The NEC requires the use of AFCIs in many residential circuits, particularly in bedrooms and living areas. Chapter 2 also covers the identification of conductors. Proper identification is crucial for safety and troubleshooting. The NEC mandates specific color codes for identifying different types of conductors, such as grounded, ungrounded, and equipment grounding conductors. For example, a grounded conductor, or neutral, is typically identified by a white or gray color. An ungrounded conductor, or hot wire, can be any color other than white, gray, or green. An equipment grounding conductor is typically green or bare. Understanding these color codes is essential for safe and accurate wiring. The NEC addresses the installation of electrical equipment. Electrical equipment must be installed in accordance with the manufacturer's instructions and the requirements of the NEC. This includes ensuring adequate working space around electrical equipment for safe operation and maintenance. Working space must be clear of obstructions and must provide sufficient room for electricians to perform their work safely. The NEC also specifies the requirements for access to electrical equipment. Electrical equipment must be readily accessible for inspection, maintenance, and repair. This means that equipment should not be blocked by permanent structures or stored materials. Voltage drop is another important consideration in electrical installations. Voltage drop occurs when the voltage at the end of a circuit is less than the voltage at the source. Excessive voltage drop can cause equipment to malfunction and can reduce the efficiency of the electrical system. The NEC provides guidelines for minimizing voltage drop, including the use of larger conductors and shorter circuit lengths. The NEC also addresses the requirements for renewable energy systems such as solar photovoltaic or PV systems and wind turbines. These systems must be installed in accordance with the NEC and other applicable codes and standards. The NEC provides specific requirements for the wiring, grounding, and overcurrent protection of renewable energy systems. The National Electrical Code is a comprehensive document that provides detailed requirements for electrical installations. It is essential for electrical engineers electricians, and other electrical professionals to be familiar with the NEC to ensure the safety and reliability of electrical systems. While specific updates and changes to the NEC are regularly issued, the core principles outlined in Chapter 2 regarding wiring methods, overcurrent protection, grounding and bonding, and conductor identification remain fundamental to electrical safety. Remember that local amendments to the NEC may exist, so it's always important to consult with the local authority having jurisdiction, or OJ, to ensure compliance with all applicable requirements. Furthermore, continuous professional development and training are crucial for staying up to date with the latest electrical codes and best practices. Electrical safety is paramount, and a thorough understanding of the NEC is essential for protecting people and property from electrical hazards. Firstly, wiring methods are key. Secondly, overcurrent protection must be properly installed. Thirdly, grounding and bonding methods must be followed per the NEC. Fourthly, conductor identification is a must. Fifthly, voltage drop needs to be minimized for optimal performance. All of these things need to be in consideration to make sure the electrical system performs safely and effectively. Remember to consult the NEC for the latest information.